Diffraction. So our goals for this session are to understand patterns like this. This pattern shows a set of parallel waves coming in from the left and hitting a barrier. And in the center there's a small opening in the barrier. And you can see that some of the waves go through there. And when they do that, they spread out. And in addition, if you really look close, you can see next to the kind of bright central peak, there's this dark region on either side, and then a kind of a lighter band of waves that comes back. And this is part of the diffraction that goes on. We'll also talk a little bit more about the history of our understanding of the wave nature of light. Okay, so again, diffraction, what is it? It's the spreading out of a wave when it encounters a single object or opening. And to really get an appreciable spread, you have to have the size of the object or the opening that the wave is interacting with comparable in size to the wavelength of the waves themselves. Okay, so we think back to our double source interference equation, d sine theta is m lambda. Then what we get is two sources sending out waves to a faraway point marked in purple. The sources are shown in red. If you blow up that little region where the sources are, you can see the sources are a distance d apart. The waves are going off at some angle theta, and then the path length difference turns out to be d sine theta. So our general path length difference equation for constructive interference was delta L is m lambda, but in this case the path length difference delta L is d sine theta. So there's one equation. Then when we say let's sort of take fill the space between those two sources with additional sources, that's our model of a single slit. So we've got a single slit of width A. That's exactly the same distance as our D was between the two sources in the double source. And what you notice here is that our equation A sine theta is m lambda is for destructive interference now. Wait a second, it was just for constructive interference. But they're for two different things. Okay? So here when we fill the space between our two sources with more sources, that's our model of the single slit, then you say, well, if the one on the right and the one on the left are a full wavelength apart, then the one in the middle and the one on the right are half a wavelength apart. So are the two green ones, so are the two orange ones, so are the two blue ones. So what you get is the waves from the right half of the opening exactly cancel the waves from the left half of the opening. This is why our equation now gives destructive interference, where it gave constructive interference for the double source. Now, what is a double slit? Well, a double slit basically is a single source like a laser beam shining on two very narrow openings that are very close together. That's what Young did in 1801, except he didn't have a laser, he used the sun, so it was a lot harder for him. We can use a single frequency source, a laser. Makes it a lot easier for us. So it turns out in that case, the double slit pattern, which you see at the bottom, this is kind of intensity as a function of position on a screen, is the multiplication of the single slit pattern at the top and the double source pattern. So the idea there is that if each slit sent out light uniformly in all directions, then you would simply get the double source pattern. Nice and simple. But what happens is that each slit sends out a diffraction pattern where most of the energy is directed in the central maximum beam. At some angles, no light at all is sent out, and then there are these little side lobes where you get a little bit of energy being sent out. Not a lot, but a little bit. Okay, so then you get interference between the two diffraction patterns, one from each slit, and that gives you this double slit pattern at the bottom. But you can get that bottom pattern by simply multiplying the single slit pattern by the double source pattern. Now, when you do that, what you find is that the equation d sine theta equals md lambda from the double source predicts that there are peaks at certain angles, and it does a very good job making that prediction. But it turns out that where that equation predicts there are some peaks, every once in a while you don't see them. We call them missing orders, and that's because that peak in the double source pattern lines up with a 0 in the single slit pattern, which means that neither one of the slits is sending out any light in that direction. Here's another view of the missing order. Okay, so you see clearly that on the left and the right, away from the center, there's a missing spot. You might expect a spot there just to fill in the pattern, and there's one missing. Okay, which one is it? Well, the center one is 0. 1, 2, 3, it's number 4 which is missing. 4 on either side. And again, it's missing because it corresponds to a 0 in the single slit pattern. You're multiplying those things together. Okay, changing gears a little bit, let's talk about history. So before 1800, Young came along in 1801 and did his experiment. So prior to 1800, people didn't quite know what to make of light. Newton said light acts as if it's made up of particles. This was his corpuscular theory. So this was around 1700, right? So 1643 to 1727 was when Newton lived. And around the same time, there was a Dutch scientist, Christian Huygens. He was slightly older than Newton, about 14 years older. And he was a strong proponent of light acting as a wave, and he had some great experiments that could be explained in terms of light acting as a wave, in fact. But lots of people chose to believe Newton, and it's not surprising because he was right about lots of other things, right? Gravity, 3 laws of motion, etc., etc. So, people were debating, what was light? Then along came Thomas Young, 1801, did this great experiment. Here's a picture from his notebook. You've got a source A and a source B sending out waves. This is the pattern you get. You can really only explain that pattern in terms of light acting like a wave, constructively interfering, destructively interfering. Okay, so then a bunch of French scientists thought this was very interesting. They did some experiments, and Fresnel was presenting some work on diffraction to the French Academy, the Académie Française, that is, in 1818. And Poisson was there, and he really didn't buy this at all. So what he realized was that if the wave theory was right, then there should be a bright spot at the center of the shadow of any round object. Why is that? Well, because waves leaving the edge of the object would be the same distance from the center of the shadow, so that would be constructive interference. You should see a bright dot. And of course, nobody had ever seen one, so that's proof that the wave theory is wrong. Except Arago went away. He was there too. He went away and he did a very careful experiment, and he showed, in fact, there was a bright spot. So that provided compelling evidence to support the wave theory. Okay, now just to prove that you can actually see a bright spot at the center of the shadow, here's a picture that I took myself. It's the shadow of a ball bearing supported by a magnetic nail. So you can see the tip of the nail at the top, and clearly you can see in the center of the shadow, nice bright spot coming from, again, the constructive interference of light rays around the edges of the ball bearing, all the same distance away from the center of that spot. So, giving you constructive interference at the center. So there you go, the wave theory of light in action. Okay, so that is it for our introduction to diffraction and a little bit of history as well. The end.